Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗪𝗟𝗟𝗟 and today we're gonna talk about a very important and crucial technique. It's the ret2libc technique. At first it might seem a bit difficult, a bit confusing, but once you get into it, you'll see that it's one of the simplest techniques you can perform. Here we have our source code. As we can see, okay, we have a helper gadget here, 𝗪𝗟𝗟𝗟𝗪, and then the main function which has a car buffer here, 0x20 initialized with zeros, printf, 𝗙𝗪𝗟𝗟𝗟𝗪, and then we have the buffer overflow here. We read from std in to buffer 0x100 bytes, which is a lot bigger than 0x20. We do not have a win function, we cannot do stuff like that. We also do not have the address of buff, like we did in the previous example at ret2libc. So how can we actually get cell? Let's first compile the program like this one and like this one. Okay, so now we have the ret2libc binary, which is without the static flag, and here the static one. As we can see, the difference here is huge. The first one is 16 kilobytes, while the second one is 785 kilobytes. And as we can see here, file ret2libc and file ret2libc static, we see that the first one is dynamically linked and the other one, the bigger file, is statically linked. What's the difference here? In simple words, the dynamic one loads the functions like printf and read, 𝗪𝗪𝗪𝗪, and the others in the runtime. The other one contains all the libraries, all the functions it wants, the addresses inside the binary. That's why it's so much bigger than the dynamic one. And let's proceed here. As we can see, we run the program. And of course, segmentation fault here, yes. So we actually have a buffer overflow, and let's find the offset. 𝗪𝗪𝗟𝗟𝗪𝗪 200, and we take this address here and run, and bam, and we see that the stack when the program crashed is like this, so 𝗪𝗪𝗟𝗟𝗟𝗪, and we see the offset is 40, nice. Okay, so we know the offset, the stack is like this, 32 bytes of junk for the buffer, and then 8 bytes for the RBP, and then at 40 bytes we start overwriting the return address. But right now we don't have anything to go here. Yes, we can overwrite it, but there is no an actual place that it's helpful to us right now. That's why we need to, let's go into the debugger again. If we run info functions here, we see that the symbols we get are printf at plt, read at plt, flash at plt, and then the default stuff. And the similarities here, printf, okay, flash, read, read. So it actually loads the functions that run inside the program. And we know these addresses, okay. The program is not position independent, pi is off, so these addresses are constant, we know them. They do not change, they do not get randomized. What we don't have something like execv, something like system, which can spawn a cell to us. That's why we need to somehow create these function calls. And how can we create them? Let's say printf, we see, okay, we know that printf is here. But if we do p_system, no symbol table is loaded. And why that's happening? Let's run the program, bmain, run, and now let's do again psystem. Okay, now it finds an address. We see libc system is here. Okay, let me zoom out a bit. And if we do vmmap, I'm gonna zoom out a lot here so it's visible. So vmmap is actually it gives us a mapping of the addresses of the binary. Here we see the start of the binary starts at 0x40 until here. This is the ret2libc binary. These addresses are all static, they are not dynamic, and this region have functions like main, have the plt and stuff. After that we see another couple of addresses here starting with 0xFFFF7FFF blah blah blah, and here it says that it is the libc until here, so this region is all libc functions. And as we can see, our system here is inside the libc, FFF7C5875. Yeah, so it can go like this, 5, 8, and 750. This one is the random part, and this one is actually the constant part. Let's have it here. So we have this, which is system, and at this run we have libc base, which is the first one here. We see that this is the first occurrence of libc. So this one is the libc base. So we have these addresses. Let's go on another run. gdb, bmain, run, and right now we have vmmap and psystem. Okay, this does not change here because probably the debugger does not randomize them each time, only once. But let's do it dynamic. LDD ret2libc, LDD ret2libc. Let me zoom in, not so in. We see here that the libc at this run is like this, and the libc at this run is like this. Okay, we see that this one is constant, actually the last 3 bytes, and this one gets randomized each time. But what do we know? We know that the system has this constant. So at this run, system would be like this, and system would be like this. This is the base address, like this, but if we convert it to this, if we add the system offset, right now at this run, the system function call would be here, and at this run it would be here. Okay, so we know that functions have some offsets inside libc. In my libc here, system offset is this, and every time the program runs, if we know this offset and we know libc base, we can call system. Alright, this is a key point we need to understand before we proceed, that functions have a constant offset. So how are we going to actually leak libc? I mean, okay, we know the offset, we know this, but we don't know the libc base that is randomized every time. This is where the GOT and the PLT come into play. In a few words, what is GOT and PLT? The global offset table, what its purpose, stores the absolute addresses of global symbols, usually functions or variables, that the binary uses but that live in shared libraries, like printf from libc. And when does it use it? When the program is compiled as pi, position independent, and it can hardcode absolute addresses. So that's why it uses a table of pointers. So yeah, GOT is actually a table of pointers to functions. And at runtime, the dynamic linker fills the GOT entries with the actual addresses of the functions. And what is a PLT? PLT is a jump table for calling external functions through GOT, enabling lazy binding. So what we actually need to do, we have the PLT functions that we can call, which was printf, read, and fflash, and we need to actually leak a GOT entry from whichever function in order to calculate the libc base. Let's try and make our solver here. So it is more clear while we're solving it. From pawn import all, and then we have our fname, which is ret2libc, and then we have elf fname, and then let's go with libc, and here we have ldd, we have this one as our libc, elf libc, and then let's make a local process fname. This one will create a local process as we saw in the previous examples. And let's start by exploiting the program. We know that our offset, the payload, should be something like BA times 40. Alright? Payload. And then the payload, this one, fields buffer and RBP. After that, we need to do something. We need to go somewhere. Where shall we go? If you remember from the buffer overflow with ret2win with arguments, there is this nice gadget, grep pop RDI. We have this nice gadget. We can simply take this like this, p64, and this one. I prefer the more dynamic ways, which is p64 rop RDI 0, but in order to do that we have to make rop e. So this one is from Pawn Tools and it will actually load gadgets. It can do many stuff dynamically, and I'm gonna use this. Pop RDI ret. And what do we want to have inside RDI? In the previous example with ret2win with arguments, we had, okay, we need an argument to put there, but right now what? We don't have any argument. We don't have something like that. What we want to do is something like call, let's say, printf that has as an argument, I don't know, let's say function 𝗪 GOT, and all this is PLT. So you actually want to call printf at PLT and as an argument have the address of 𝗪 at God. That means our RDI should contain address of this, of 𝗪 at God. Instead of 𝗪 at God, we could do another function like read, like whatever. I just chose this so it's visible. And printf at PLT This one is already known, as we saw here, printf. We already know this address. Let's try and create this. So RDI is the first argument, so we need this address. I'm gonna do it dynamically like this. 𝗪𝗟𝗟𝗟𝗪 from E that we have analyzed here, go to the global offset table and take the address of 𝗪. Take the address of 𝗪 from got. Okay, this one is a big, okay, like this. So we have this right now, and what we want, okay, we have our RDI ready, but we actually need to call printf. So here we're gonna have payload p64e_plt printf. So we call it go again to E in the PLT, in the procedure linkage table, and take the address of printf, or we could actually just insert this here, address of printf from PLT, and after that we need, where do we need to go? Just exit? No, we actually need to loop back to the program, so we're gonna do payload p64e.sim main, return to main. So the program will loop again, r.sendLine payload and print. Here we need to leak the address, leak libc address, if everything went smoothly. So print, I don't know, r.recline. This is a bit trial and error here. So let's run the solver. Fill me up, 𝗪𝗟𝗟𝗟𝗪. This one is not correct. Let's try again and do r.reclines 1. Okay, it read nothing. Why though? So here we have fills the buffer, p64 rob RDI, egot 𝗪, eplt printf, and esim main. This is our payload, and we send the payload. Send line after. I don't think this is a problem, but let's try it. Nope. Maybe it needs a stack alignment. So let's try and do some payload p64 and let's go with rob ret0 return gadget for stack alignment, ret gadget for stack alignment. Okay, let's see if this one is better. No output, why though? Yeah, okay. Here we see a leak. Yeah. You see that we leak the address here. But why it's not, why is it printed like that? Print r.recline. 𝗪𝗪𝗪𝗪. Okay, this one worked for some reason. Rect until fill, and we need to drop 4. 1, 2, 3, 4. So yeah, here we have our leak. So let's say this is our leak. And okay, this format of course is not something meh. This is not something we can read like this. What? Oh, okay, I don't print it. So we actually need to, let's print leak. Yeah, so we see that this one is actually 1, 2, 3, 4, 5, 6, 7 bytes. This is not an 8-byte address, so we're gonna adjust to it. Just 8 bytes. So we're gonna fill zeros until it is a full address, like this. Okay, here we see this better one, and we actually need to convert this. If you remember from the previous videos, this is 𝗪𝗏𝗟𝗟𝗏. So we used P64 to convert the hexadecimal values to this. Now we're gonna do unpack64 like this, which is exactly the opposite. So it takes this and creates a nice integer, and let's have it in the hex format like this. And nice, we have a nice function here, which is leaked f__ at GOT. Yeah, nice and cool. And this one is a libc address. Okay, and as we can see, the offset is constant. We have 857F0, 857F0. So this one is the offset of f__ inside the libc. The rest ones are always randomized, but this one is constant for this function. Okay, if we change the function, and for example here we do, instead of f_, let's do for example read, like this, we see 1BA50, 1BA50. The rest are randomized, but this one is constant. Okay, we can work with read. Let's go with read. Right near. No. I'll keep it as it was. So we're gonna work with f_, but as you saw, it doesn't matter. We could use read, and it's the same. And right now, we need to find the libc base. How are we gonna find the libc base? We already know the libc that the challenge is using. It's this one, and we're gonna do libc.address, libc address, and here calculate libc base. So what can we do? We can go with the leak we have. So imagine this address, and we do libc symbols and take the f__ function here from inside the libc, and if everything went correctly, this one should be the libc address, the libc base address, libc base and it's libc.address like this. And as we can see, these ones, the random ones here until 4 are the same and the rest are zeros. That means we actually found the libc base. How can we also calculate it a bit manually? We go inside the debugger and we do vmmap, bmain, run vmmap, and let's say pf_. We have this function here, and we do px for hex values, and we have this minus the libc base address, which is, oh my god, which is this, and we found the offset. So this is the offset of f_ inside libc, inside my current libc. And if you do the opposite, if you have your address again like this and you subtract this, you get the libc base. So this is exactly what we did here, but dynamically. We lick the f_, this one, which is not known when we run the program, and we subtract this one, which is known when we start the program, and get the libc base address. Okay, now that we have libc base address, what can we do? We can actually find and create a system call. So here, perform a ret2libc attack. Now, instead of that, we need to do something like system bin sh. We need to actually call something like this. RDI should be the address of bin sh, and we can continue like this. It's the same procedure. Again, we're gonna go take this, and then we have the RDI gadget again. But now instead of got f_, we need the address of bin sh, which is I think it's something like next libc search bin sh. I think it's something like that. If no, the program is gonna tell us. And after that, we're gonna have, I don't know if we need a red gadget here, but we can go with payload p64 and libc symbol and system. So this one works the same. As we said, the libc changed its base address with what we found. So now we tell the program, okay, go to the libc, and from the symbol table, find me the address of system. And let's see if this is gonna work. If this works, we're gonna get cell. Oh, and it worked. Bytes warning, okay. Let me just, I don't want the errors, I want you to see the output clean. Some new lines here, some new lines here, and a byte here. And as we can see here, a bit cleaner, we leaked a flash at GOT at this address, and we have a libc base at this address, and we have cell. Who am I? So this, guys, was the ret2libc attack. I mean, okay, it may seem a bit confusing, a bit tricky, a bit difficult in the beginning, but I think we analyzed it a lot in depth to understand how and why it works. If you guys found the video useful, leave a like, leave a comment for feedback if you have any questions, if you didn't understand something, and see you guys on the next video. Bye.